Yeah, okay, now you can start.
Okay, so I'll share my screen.
Yeah.
So you can see the screen, right?
Yeah.
Okay, so for today, I'm gonna do a paper review, and the paper is called the elliptical slice sampling. And the elliptical slice sampling is kind of the MCMC sampling. So this is the outline for today's session. So for the first part, I will do a brief review of the MCMC, especially focusing on the detail balance. This is because the proof of the eclipse slice sampling is based on the detail balance. And then I will do a brief review of the three MCM samplings. They are Metropolis Hastings, Gibbs, and the slice sampling. So they're also very important because the elliptical slice sampling, this paper, the start point is from the Metropolis Hastings. And then this paper will also use the shrinkage trick, which was first brought up from the slice sampling. And then for the second part, I will do the review for the model itself. And then for the last part, I will review the experiments and the results. So the author compared the model with other three samplings methods. So the three methods are line slice, neo MH, and the control point MH sampling.
Yeah, I
Okay,
just want
so
to I just want to emphasize one point. So the reason I asked Dad to present this elliptical slice sampling because it turns out to be a very effective approach for the Gaussian process inference.
yeah.
So especially the latent Gaussian models. So you can imagine you use a Gaussian process to sample function, then the given function you sample the observations. So actually, our previous project we have a some issue. We found that the MCMC doesn't work for a little bit more complicated Gaussian process models. Like you have to use variation inference or even use map estimation. So I asked Dad to present this. Hopefully, we can leverage this approach to make the posterior inference of Gaussian process working.
Yeah, so okay, so the first part is the MCMC. I think you all know so there is after the burning stage, the Markov chain will converge to a stationary distribution, and such that it will satisfy the detail balance. And this is the definition for the detail balance. So this pi here is the stationary distribution. So it means from the step I to the step I plus 1, the distribution is the same. So it means it reaches the detail balance. And the second equation is a more straightforward and more understandable equation. This is the equivalent to this equation. So if you can approve the detail balance is correct and then the MCMC sampling is correct. So this means this is the stationary distribution, and this is the transition distribution. It means the probability at I times the probability jumping from I to J is equal to the probability at J times the probability jumping from J to I. And it's very symmetric, yeah. And then, so then is the Metropolis Hastings sampling. So we need to construct this equation to have the detail balance. So, but it's not easy to find a perfect transition distribution. Instead, in this method, so So we need to use a proposal transition distribution. And if you plug the proposal transition distribution into the detail balance equation, obviously it will not equal. So instead we can multiply the first term by this factor, and then both sides will be equal. Also, this is called the acceptance rate. Okay, this is the algorithm, so I will not go through the details.
Now you should give a better explanation of this. So the metropolis testing essentially is to construct a transition kernel or a proposal generation which satisfy the detail balance. So here P of xi to x star is the initial proposal. I mean, usually people just use some Gaussian for continuous variables. But if you simply do that, it usually doesn't satisfy the detail balance. That's why you have to add an acceptance test.
Yeah, this is the acceptance test, the acceptance rate.
If you multiply the acceptance test with the initial proposal distribution, this whole will serve as the transition kernel, or the way to you generate really generate the proposal. Then it satisfies the detail balance.
What is the Q of star given xi in the algorithm?
Where?
In the algorithm, the second line in the algorithm.
Oh, you mean this one?
Yeah.
Oh, I'm sorry. This is actually the P. So it's the P here. It's the proposal distribution, transition distribution. Yeah. So the procedure that you first sample U from the uniform distribution, and later we will check the U if it's less than the acceptance rate or larger than this. If it's smaller than the acceptance rate, and then we'll accept the sample. If not, we will not accept the new sample. We just keep a copy of the current sample. Okay, and then the Gibbs sampling. So the Gibbs sampling, you can view it as a special case of the metropolis Hastings sampling. And the Gibbs sampling is just used to sample a multivariate probability distribution. Okay, I also will not go through the details. And then the slide sampling. So the idea for the slide sampling is that we can sample from the region sample from the region under the density function. So for example, this is the distribution, and this is the density function, and we can uniformly sample from this region. And the x coordinates is the sample that we want. But how to do this? So we will use auxiliary random variable and denote the height as the u. So the joint distribution for the u and x is a uniform distribution. And we can prove that is marginal distribution is equal to the fx. So this is the slide sampling. And how to do the sampling? So since the joint distribution is a two-dimensional distribution in this example, so we can use the Gibbs sampling here. So the Gibbs sampling is to sample one dimension at a time. For example, we first sample x, and then some u, and then some x. So repeatedly like this. And then, so let's give an example here. So let's assume our current sample is here, xi. And now we want to sample the u. So you just go through the xi and make a slice here. And the u region is this line. And you want to do a uniform sample from this line. And let's assume that we get the u here. ui plus 1. And then you go through the ui plus 1, make a slice. And then the valid sampling region for the x plus I plus 1 is this region. And you sample from here. So that's the sampling procedure. And you do the sampling repeatedly and you get the samples. But here there is okay.
What if the u is slightly higher?
You mean higher like here? Oh no, like here. You mean here?
Yeah, I mean it crossed the two peaks.
Oh, you mean?
You happen to cross the two peaks. Yeah, yeah.
Here. Okay, so you need to find the valid sample region is the x where fx is greater than the u I plus 1. So is this two place.
Then you need to solve the equation to find out the
Oh no. This is what I'm gonna talk about. So this is the problem, right? Like you need to find which region you want to do the sampling. So there is a shrinkage trick will be used. So
the joint probability, that before we go on, we need to specify the joint probability. So the P of u and x is that like given x, u is a uniform from what?
Given x, u is a uniform
from 0 to f of x.
Give x the u is u is the from 0 to fx. Yeah.
And giving u, what is x?
Given u, x is the you need to sample the region where the fx is greater than u.
Okay, so what's the definition of a joint distribution of x and u?
So the definition is this region under the density function. So the P of xu is 1 because the area is 1.
One times what? There's an indicator, right?
No, just 1 because the area is 1. So the PXU is 1. It's a uniform distribution.
But what's the domain for x and u?
Oh, the domain is the region under the density function.
So the joint probability will happen to be constant 1, and then if we marginalize x, marginalize u, then we will have the px to be the desired distribution.
Density function. Yeah. And since this is
it's better for you to give how the structure of the P of x and u.
I haven't looked into the details, so.
Okay. Anyway, we'll cover it in our probabilistic machine learning class.
Okay. So, yeah. So So just like Panjimeng said, there is a problem that we need to find the valid region to get the sample. So there's a trick called the shrinkage trick. So let's assume that we have a very complex distribution. And then we have the current X here. And then the U is here. And we want to sample the valid xi plus 1. So let's assume that we don't know the valid region is these two lines. So first we need to do a uniform sample from the sample space, the whole sample space. So let's assume we get the sample here. And then we need to do the shrinkage. So we just discard all the region before the xi plus 1. So we just sample from this region. And then we do a uniform sampling from this region. Let's assume we get this place. This is our candidate, but it's obviously is not a valid. So we will do the shrinkage again. So we will.
I'm slightly confused just on one thing. Sorry to interrupt you. What's the upper bound on sampling from X? That's the part that I'm like, how do you determine the upper bound? I see that you've drawn the lower bound from xi plus 1. Maybe, I don't know if that axis indicates 0, but you've drawn it below where maybe someone would think it was 0. But then how do you determine the upper bound where you could draw from in the uniform distribution?
This is the bound. So given a u I plus 1, you need to find the region where the fx is greater than the u. Like here, given the ui plus 1, and this place, you can see the density function is greater than the ui plus 1. So
Okay.
this region is valid. Okay, so we get the second candidate, but it's not valid. So we need to do the shrinkage again. So we just discard the region between the last sample xi and we just discard the region after the xi plus 1. So the remaining valid sample area is this part.
First, I have a question. How do you sample uniform sampling from a infinite range?
I'm not sure. Yeah, I just read the procedure, so I don't know how they do that.
This is actually an issue. You always need to have the bounded support. I mean, or at least you need to specify the boundary of the support of the interest. Otherwise, you cannot do that. Like for example, I'm just interested in -10 to +10. Now I do this. I restrict my sampling inside this range.
How do you know every time you will be able to sample, like the resulting area is still valid? So if you like, what can I annotate here?
Yeah, if you get the sample I plus 1, you just plug this into the fx to check if it is greater than the u.
So suppose the first point is slightly to the left of this point, then you will have a like
shrinkage. Yeah.
No, like I want to draw. So suppose your second point and your first point is slightly to the left of your second point, then the remaining area will be unavailable for your next step, right?
Would you repeat? I'm not sure what do you mean.
So your row is the first point is to the left of the two peaks, but how about the first point you sample is located to the right of the two peaks.
Oh, you mean the first sample is here?
Yeah.
Oh, so you just discard because you need to look up to the current sample. So this is the center, and you just want to discard the area that away from the current sample, because you can always make sure the current sample is in the valid region. So if the first point here, you just discard all the region after this, and this part will be the valid region. Or this part will be the current sampling region. Yeah, so you just so you repeat this shrinkage, repeatedly do the shrinkage, and then you can get the valid sample from the valid region. So this is the shrinkage trick.
There's a problem here. Actually, you don't know whether you're gonna discard region on the left or on the right, right?
You can decide, because I think you always know the current sample is you know the new sample is to the left or to the right of the current sample, and the current sample must be on the valid region. So you can decide the left to discard or the right to discard.
Like the right sample xi plus 1, the most right sample you just draw, and you don't know if a valid sample should appear on the left or on the right. It is possible that you have a third peak, a third mode to the right of xi plus 1, right?
To the right of I plus 1.
Yeah, if you draw another peak.
Oh, yeah. So in this way you can discard the valid region. It's possible that you discard the valid region. For example, if the xi plus 1 is here, and you need to discard all of those.
Yeah, that's the major reason, right? So actually, as long as we can figure out a way to find one sample in the valid region, that's it, right? So it's possible to discard the right region, and they also to discard the left region.
What do you mean?
Could you?
In this case, you can choose to sample uniformly from xi plus 1 to the right bound, or you can choose to sample again between xi and xi plus 1. I mean the left part.
I'm not sure, but the shrinkage trick that I know is that you need to know the current sample is here, and you will not discard the region around this current sample.
We have a description of algorithm. I'm not very clear about this process.
I don't have the procedure, so I just roughly read the slide sampling.
Yeah, that's fine. I do believe the way to find out a region, a valid region sample is not like it should be some recursive, like a binary partition procedure rather than this. I mean, which material did you read? Is that PRML book?
No, it's just from YouTuber.
Okay, I think it's a two-way. It's not because it actually tries to like using a recursive way find a sample in a valid region. That's it. As long as you can find a way, find a sample in that way, then you are done.
So basically it's a Gibbs sampling procedure, right? For the flash sample.
Yeah.
Sampling the
sample.
X and sample the X and U alternatively.
Yeah, it's a Gibbs sampling for it's multivariate distribution. So we use a Gibbs sampling, right?
There's one major limitation that it has to make sure the X is under the curve.
Yeah.
And find the root of a curve is very costly or even impossible for a complex function. Then there's like some shrinkage trick, but I'm not very clear about how the process goes. But maybe I believe they are valid anyway.
Yeah. Okay, so let's continue. So now is the elliptical slice sampling. So before we get started, I just want to say the eclipse slice sampling is actually just used to do the sampling from a kind of the distribution. So the distribution must have the prior, the multivariate Gaussian prior. So so the paper, the starting point is the neo-MH sampling. So this is the neo-MH sampling for the multivariate Gaussian prior.
The L here is
So
the likelihood function, right?
Yeah, L here is the likelihood function. And this is our target distribution that we want to do the sampling. So this is the prior and this is the likelihood function. And this is the neo.
Was f is a function or it's some value?
It's a vector. Like Gaussian process.
Yeah, it's a vector.
It's a vector.
Yeah, it's a vector.
Gaussian random variable.
Yeah. So the neo-MH is like this. So F here is the current sample and the F prime is the new sample. And you can, and the V is from the prior. The V is from the prior. And you can think of this function as a transition distribution. And this epsilon here is the step size parameter. And you can say if the epsilon is bigger and is is smaller, is near when is near 0, the new sample and the current sample is very similar. But if the epsilon is large, when it close to 1, and the current sample and the new sample is not similar. So the epsilon, the step size parameter, determines the difference between the current sample and the new sample.
What's the why the acceptance test only needs to calculate the ratio of the likelihood?
Sorry,
this would be LF.
Yeah.
Because P of F prime given F is the same as P of F given F prime.
Yeah, this is the acceptance rate. So as you write in this, and then you can, these 4 terms are canceled, and so just the likelihood left. So this is the likelihood, and this is the prior, and this is the transition distribution, and then it's canceled. So it's just the likelihood left.
One second.
Okay.
Let me take a look at the acceptance rate. So actually it's V, right? Because
yeah, is a V here.
So we have prior V, which is Gaussian. Then given V is equal F prime.
But since here the F here is from this normal, so when you add them together, so the transition distribution is also a normal. Just see like.
But here you should get like P of V and then no, it's P of F times P of F prime given F, right?
Yeah, you can do it that way, but I think I can also like add them together and use this distribution.
That's the marginal. The F prime, that's the marginal distribution of F prime. I mean, to show the detail balance, you have to look at P of F and then jump from F to F prime.
Yeah,
This should be the independent chain metropolistic. It can be a independent distribution. The transition distribution can be independent from the previous sample.
Yeah, no, V and F are independent. But F prime essentially is a transformation of F, right?
Yeah.
So what's the conditional probability of F prime given F?
F prime give F is the is the about V.
Is it Gaussian? Because it's the like a affine transformation of a Gaussian.
F here is constant, right? F here is constant, so the conditional mean will still be 1 minus epsilon square root times F, and the variance will be epsilon square times sigma.
Yeah.
Epsilon square times sigma. And then you need to do this. Yeah, I guess it will cancel anyway, but it's better to follow the strict definition. Like you starting from F, you jump to F prime. You starting from F prime, you jump to F.
Okay. Yeah.
Or if you will, in another way, like you starting F and V, okay, F prime, and the likelihood is essentially the summation, the weighted summation of F and V.
Yeah.
At the in liquid, that might be correct.
Yeah, because the F is also a random variable, so it has the normal prior distribution. So that's why I added them together.
Okay, yeah, let us continue. Let us continue.
So the transition kernel here, V is we follow the Gaussian as the prior over F.
Yeah, so the V here follows the same prior as the target distribution.
So we pre-specify this prior just as the prior of F, like in Gaussian, like in GP.
Yeah, you just like it's the same prior as the GP. Yeah, here.
Okay, nice.
Okay, so in the neo MH sampling, so you need to very carefully choose the epsilon, the step size parameter, because I think there is a problem called the mixing problem. So like we have a complex distribution, and then like let's say our current sample is here, and so the current sample will tend to jump to a high density area. Like if this area the density is very low, so it's very hard for the xi jump to si plus 1 here. So it's very hard for him to jump to here. So in the end you might not get any samples from this area. So this is called the mixing problem. So especially when the step size is very small, so it's very hard for it to jump to this area. So in the near MH, so you need to choose the step size very carefully. And usually during the training, maybe you need to use different step size parameters. So the motivation for this paper is that the author wants to have a model that can automatically search over the step size parameter. So this is what he does. So he makes the step size parameter as a random variable. This is the model. So if you substitute with the epsilon with the sine theta, you will find these two almost equal, but they are not equal because the range of the sine theta is from -1 to 2, 1, and I'm sorry. This range is from -1 to 2, 1, but this range is not less than 0. So actually, the sample region for the new sample is larger than the MH sampling method. So it gives a richer choice for the new sample.
What is theta here?
Theta is a auxiliary random variable. So theta is from 0 to 2 pi. And as you can see, as you vary the theta from 0 to 2 pi, and the trajectory of the f prime is actually an eclipse.
But theta follows a uniform distribution.
Yeah, theta follows a uniform distribution from 0 to 2 pi.
And we still sample V the same way, and then we multiply by another random variable here.
Yeah.
Yeah, the eclipse of theta.
Yeah. So this is the acceptance rate is the same, is also the likelihood division. So the model, the sampling procedure is here. So the graph from A to D is the sampling process. So first you sample V from the prior, and then you sample the U. So the U here is used to check if the U is less than the acceptance rate. And you can the check is here. So the check, it checks greater than log L f plus log U. So it can, so it's U less than. So this is the check. If the U is less than this acceptance rate, and it will accept the new sample. So the procedure is like this. So this is the eclipse. As you vary the theta, it will give you eclipse like this. So, okay, so this is the current, the black cross means the current sample, and the red cross means the V. So you construct a eclipse through those 2 points, and you started do the sampling. First, you sample theta. You sample uniformly from 0 to 2 pi. And let's assume you get the first sample here. The first choice here. Oh, sorry. this green line means the valid sampling region. It means for those points, the acceptance rate is less than the acceptance rate. The U is less than the acceptance rate for those green line area. Okay, so the first choice if you made is here, and then it's not on the green line. So you need to discard this choice, and then so the second step, you do another uniform sampling from 0 to 2 pi. Let's assume you get the second choice here. It's also not on the green line. So then from the second step, you started doing the shrinkage. Since the current sample is here, and you need to discard the region from this point to, let me see. You need to discard the region between this and the last sample here.
Why do you use this shrink procedure? I mean, go back to
What do you
the
mean?
previous slide. Yeah, first of all, we need to be clear what's the distribution here, right? So you have an augmented model with a uniform random variable theta. And then you got acceptance rate. But this acceptance rate is just to accept the new sample of f prime, right?
Yeah.
And then given f prime, you sample theta again. So this is like a Gibbs sampling is like alternating Gibbs sampling like procedure. Like you first given theta, you sample f prime, and given f prime, you sample theta.
No, this so for this algorithm, so you first sample a U from here, and then you repeatedly sample the theta until you get the valid sample that the acceptance rate is greater than the U. I think it's kind of different from the previous slide sampling.
That means you just adjust the theta to ensure.
Yeah, it just adjusts theta to. Yeah, you're right. Yeah, you just adjust the theta to until you get the valid sample.
Why is this valid? I mean, is this still I mean, is it under the slide sampling framework or?
I think it's different from the slide sampling, but they just share the shrinkage trick.
It seems like they are doing the other way around. They first determine the accepting conditions and then sample and then keep sample until the condition is met.
Yeah,
like
they first sample the threshold.
They just keep sampling theta until the acceptance test is passed.
Yeah.
They keep adjust the theta, not sample the theta. Or adjust the bound of theta.
Yeah, later I will give the proof for the detail balance. The detail balance is satisfied, so. It's a valid sampling.
Okay, let us look at the detail balance part.
Okay, so you just discard this region and you do the sampling from the left eclipse, and then let's assume you get the third sample here, and then it's not on the valid region, so you just do the shrinkage again, and you shrinkage from here to here. and the valid sample region now becomes here. And now you finally got the valid sample right here on the grid line. Yeah, this is the sampling procedure. And now I'm gonna do the proof. So this is the detail balance. And first, we define the VK and FK here. So the case from 1 to capital K. So this means the choice that we made during the sampling procedure. Like at capital K, we get the final sample.
Final sample of theta?
Yeah, final sample of theta. So the theta K is the final theta we get. But the K from 1 to K minus 1 is the choice that we made, but we discard them.
Okay.
Okay, so to prove the detail balance is correct, you can think of the two terms as two procedure. Like the first term is how you jumping from the let's assume that this is the current sample and this is the weight. And let's assume our last sample is here. This is the sample we get. And this is the weight defined by this one. And the first term, you can think of it as either jump from F to F prime. And you can think of this term as the procedure jumping from F prime back to F.
Yes.
And then, yeah. So you need to prove that the probability at the current sample times the probability from jumping the current sample to the final sample is equal to the probability at the final sample times the probability jumping from the final sample back to the current sample. You need to prove that equal.
Mm-hmm.
So we define the current sample as F and V, and the final choice that we made as F prime and V prime. And you need to prove this, they are equal. So, and this probability for the current sample is this one. This is actually a prior times the likelihood, and there is a constant here. And this part is the probability you jumping from the current sample to the final sample. As you
of y given f.
So the y is here, is this one. So if you times them together, the log of y is equal to log L of times u. Since the u is from 0 to 1, and then y is from 0 to f logically. So y is also a uniform distribution at 0 to LF.
Oh, okay.
So y, yeah. So the v is the transition distribution, and theta, those theta from 1 to k is the theta that we use during the shrinkage. This is the same for the reverse procedure that we jumping from the final state back to the current state. So it can be written like this. And then since for here the PYF, since it's a uniform distribution and the probability is 1 divided by LF, so it can be cancelled with this this place. So it just this equation left.
Also, the likelihood term is vanished,
Cancelled, yeah. Yeah.
and V prime are sampled independently from the prior.
Yeah.
And when you sample back, the theta k doesn't change. I mean, the joint probability of those theta k's don't change.
Yeah. So yeah, you're right. So to prove this is equal, so the paper like breaks them into two parts. So they first show this part is equal, and then I'm sorry, and then they prove this part is equal. So the delta balance will be equal. So to prove this is equal, you can just use the Jacobian transformation to prove this.
Okay.
So yeah. So VF is a random variable, and VK and FK is their functions.
Okay.
Function
So,
of the
okay,
V and F.
okay. So this is a shear transformation.
Yes.
Okay.
Yeah. So these are equal. Also, you can prove this equation is equal because for all the theta, they are just the uniform distribution. And when you do the reverse procedure, jumping from the final state back to the current state, you will find those theta are all equal. So that's why they are equal.
But is it the probability always 1/2 pi? I look at the algorithm.
No. No,
it
it's not. It's just the first two choice you made is one is 2 pi, 1 divided by 2 pi. But for the others, because you shrink the eclipse, so it will not be 1 divided by 2 pi. But they are equal.
Okay, as long as it's reversible, it's
yeah, this is a reverse procedure. Yeah.
But how do they guarantee that by using this shrinkage procedure, they can always find a theta which pass the acceptance test?
Because the current sample is the black cross, and you always do the shrinkage that away from the current sample, and the current sample is always inside the valid region, like the green line. So you will not shrinkage out this region. So that's why you can always get a valid sample.
What do you mean by valid range?
The valid range is that the region that can pass the acceptance check.
I think as they keep shrink theta, it will go to 0 eventually. Then it will satisfy the acceptance condition anyway at the end.
Yeah.
Yeah, but can I take a look at algorithm steps again? I want to make clear about the shrinkage procedure. Okay, so if you fail to pass the test, you're gonna shrink the. So at the beginning is it is 0 to 2 pi, right?
Yeah.
And then it makes the bracket to be theta minus 2 pi to theta. So can you explain the shrinking procedure again?
So okay, so the shrinkage means so this is the current sample, and this is the V. So for the first two choices that you just sample from 0 to 2 pi, and let's assume you get the first sample here, and the second sample here, and then you start the shrinkage.
And the green part are the
valid region,
which accept the test, which pass the acceptance test, right?
Yeah.
Okay.
So from the first two choices, and you can see there is no, they are not on the valid region, so you just discard this part. You cannot discard this direction because you cannot discard the region that contains the current sample. So you just discard this part. So now you can sample from this region. And this is your third choice. Is also not on the valid region. So you start the shrinkage again. So this time you starting this point, and you will need to think, you decide which direction you start the shrinkage. But since this current sample is here, so you will not discard this part. You just discard from this to this part. And now this part becomes the search region, and finally get this valid sample.
How do you decide? It is determined by the sign of theta, right? If theta is less than 0, then you set theta mean equals to theta.
Yeah, you can. Yes, you can follow this procedure, but I think it's not so straightforward. So
if you think of in terms of a theta, say if you see the fifth line, the condition is the new log likelihood is greater than the log y, which is the O log f plus minus some term. So if the new point is exactly the O point, then this condition will be met. Right. Log f will always greater than log f plus log u, because log u is negative.
Yes, I also have a question about u. Why would they restrict u between 0 and 1?
To make sure if the theta is 0, then you will get the new point as the O point f. F point is f. Then because u is within 0 and 1, then log f will be negative.
Log y will be smaller than log f. So they just want to find f prime such that log f prime is bigger than log y.
So in the extreme case, if they shrink the theta to the 0, then the condition will be they will have a always valid condition, like the new point to be the O point. So it won't loop infinitely here.
So does that mean like you actually want your sampled f prime to be closer and closer to f?
yeah, to the current sample. So you will not discard the region,
and you just
that,
discard the region
away from the current sample.
Okay. Okay. Yeah, it assumes that okay, there is some continuity here, like surrounding the current sample, there must be a valid region. You just want to ensure your new sample to fall in that region.
Yeah.
I'm not exactly sure if what you described here is consistent with the line 8 to 9. Is the same thing? Because it just said, okay, if theta is less than 0, we're going to set theta mean to be theta. Otherwise, we set theta max to be theta.
I think it's the same because the graph is also from the paper, and there is a caption for the graph.
Yeah, I think the idea here is let's draw a sample and jump to another point. If the point has a higher probability, that's good. We accept the point. If the point we jump to is not having a high probability, then we will we shrink back to our starting point. And the procedure makes sure that we will always have a backup choice, which is the original point.
Yeah, then limit it will converge to f.
But it will first try to jump to some higher probability area.
Oh, okay. I mean, that I expect that you're gonna explain. So okay. So when you set theta to be 0, then f prime will be f, right?
Yeah, yeah. So
If
this
theta
is
is,
the
yeah,
this
if
is when
theta
theta
is
is
bigger than
0.
0, if theta is bigger than 0, and I assume you're joining some samples on the right hand side. Is that true?
Sorry.
I mean, if theta is bigger than 0,
Mm-hmm.
that means your sampling, your new sample f prime or new proposal f prime will be on the right.
Yeah. You
That's
mean
why
this?
that's why when it is outside region, we're gonna set theta max to be theta, because you want to draw new theta to the left of the current proposal.
Yeah.
And if theta is less than 0, that means and it also is outside of valid region, that means your new proposal is on the left. That's why they set the theta mean to be theta. That means you want to draw a new sample on the right of the proposal.
Yeah.
Does it make sense? I mean,
Yeah.
and anyone else? I think I finally got their idea why they set is theta less than 0. They want to set theta mean to be theta.
I'm still pretty fuzzy on that. Could you explain that again? I didn't quite catch that.
Okay, so the basic idea, I mean, the key idea is that they assume that, okay, surrounding f, the current sample, there will be a valid region, that is the green part. As long as you find a new proposal f prime within that green curve, you win. You generate a new sample. But the problem is that how do you ensure you're gonna find a proposal which rightly stay on the green part, which contains the current sample f?
Mm-hmm.
So if we set theta to be 0, you actually do nothing. You just stay on the current sample f.
Mm-hmm.
But theta is a uniform, right? You just sample theta. So now you can imagine you got some sample of theta which is bigger than 0, then your new f prime should be on the right of f.
Yeah.
You can random draw a location. Like,
But since it's a circle, though, doesn't it? I mean, it could.
that is determined by their polar like system, polar coordinate system. If theta is bigger than 0, then your new circle should be on the right to the current sample f. So now you want to.
You'd think that, but if it's like, what if it's like really close to 2 pi, but it's not quite 2 pi? It's a little bit less than 2 pi. Wouldn't you just be slightly to the left of the point of f?
If it's like 2 pi minus 0.01,
Yeah,
it will still be slightly to the left.
yeah. Okay.
So you can imagine this is actually a polar system, right? Polar coordinate system.
Yeah.
Well, yeah. The x-axis corresponds to a horizontal axis, and y-axis correspond to the vertical axis, which are orthogonal to this ellipses.
Okay.
So if theta is bigger than 0 and is out of this green region, so you want to draw a new theta to the left, right? You don't want your new theta to beyond the current theta.
I don't think they care about the direction. The idea of the mean and max is to keep the bound shrinking.
Yeah, that's what I was thinking, is that's what it, because yeah.
and they want to keep the point shrinking around 0, not like into a positive. So it will keep swinging left and right and determine whether you determine like by the theta. If your new sample theta is in the positive, then it will be the new positive bound, the upper bound. If your new sample theta is negative, then it will be the lower bound. But it will keep string the two bounds toward 0, but always contain the 0. You don't want the bound to both the upper bound and lower bound to be greater than 0 or lower than 0.
I mean, you can understand in that generally in that way, like the effect is trying to shrink that bound, but you need to know why they kind of doing this. They kind of like finally force your theta will be in that green region. If theta is bigger than 0 and there's all of that region, I'm gonna sample new theta on the left. So that's why they set theta max to be theta. If it is theta is less than 0, but all of the green region, that means 2 left. Next time I'm gonna find a new theta on the right. That's why they set the theta mean.
Oh, okay. I see.
Yeah.
Yeah, that's the same idea, but I mean, what they said is around the original point there will be a valley region, and somewhere away from the original point there will be another.
Their basic assumption is that okay, surrounding the original location, there is this green region. As long as you find a theta which touch that region, you got a new sample.
Yeah, that makes sense. Okay, cool. Thanks.
Yeah, that let's continue.
Okay, so
yeah, so I have one question.
Mhm.
Yeah, so can you go back to the algorithm? Yeah, so yeah, I think from this from the discussion, I think so actually there is a basic conclusion that of course this sampling would be better than the random sampling around the original theta. So I think it's because it cannot just explore the values around theta, but it can also explore some value far away from theta. So it is to have some value, to explore more value which far away from theta. It's achieved by the step 4, right?
You mean you can sample from here?
Yes.
Yes, you can get here.
I mean, I mean, in which step can guarantee we can go to the location far away from the original theta? Is that step 4?
If you like, the first choice you made is from 0 to 2 pi. If your first choice is on this line, and then you get the sample from here, and just end the shrinkage. There's no shrinkage at all.
I think she meant to ask, yeah, your question. I mean, your statement is correct. The fourth line, it will let you to explore some distant area or far away from the original F. And if the area is not feasible, then we'll start to shrink from that. Not that you first need to sample V. We still add a V here. It's not only theta.
Okay.
Yeah. Okay. So this is the experiments. So So this paper, it compares the model with other 3 sampling methods. There are line slice, new image, and control point image. And they did 3 tasks. This first one is the Gaussian regression, and it used the input dimensions from 1 to 10, and the data size is 200. And then the second task is the Gaussian process classification, and it says it's a USPS classification problem. And the third is the log Gaussian Cox process, and it's a model of the days of the mining disasters. And
So
this
is
is
the
the
Cox process the log of Poisson? I forgot it. I just want
I think the paper mentioned the Poisson, but I don't know what is the Gaussian process, so I didn't go through the detail.
Okay.
Okay, so this is the experiment results, and the first one is the Gaussian process regression, and he just get so he compared the log likelihood as the iteration goes on. So the above graph is for the 1-dimensional GP regression, and this one is for the 10-dimensional regression. So as you can see, for the 1-dimensional, as the iteration is 1000, they are almost the same performance, but during the iteration, the elliptical slicing is more stable. And for the 10-dimensional regression, the paper said the control variable almost failed, so it doesn't change.
What does it mean by control variable?
I think is a sampling method, control variables.
Okay.
Yeah. And this is the graph for the 3 tasks. So you can see from R01 to R010 is the regression problem, varying the input dimension from 1 to 10. And this is the classification problem, and this is the Cox process. And the paper used 3 measurements: the likelihood evaluations, this is the number of likelihood evaluations, and this is the CPU time, and this is the effective samples. And the number below the bars means the scales. And this is the experiment setting. So they collect the effective samples from 10 to 5 iterations after 10 to 4 burn-in. So for the effective samples, as you can see, most of the experiments, the elliptical size sampling is better than other 3 methods.
So it is the first bar. It is the first bar or last bar. First.
Yeah, the first bar means the elliptical slice sampling.
Yeah, but for the first experiment, R01 looks like it is the control point.
Yeah, it
has the better.
Yeah, yeah. For the low dimension, the effective samples, the control point image is better. But when the dimension is high, the control point image almost failed.
So do you mean that dimension is a dimension of the Gaussian prior?
Is the dimension of the input. Yeah.
Dimension is the
dimension
of f.
Yeah, dimension of f, the input. Yeah.
It's not input. It's the dimension of Gaussian distribution.
Yeah. Okay. So yeah.
What does it mean by like time 1,598, 1,000?
Oh, this is the scales for the like the number of samples and the CPU time. The CPU time is in seconds, so the scale is like 110 seconds times the.
Okay, for the first row is like 1,598 samples.
Yeah, samples. Yeah, right.
The training samples.
Oh, I think they had a description about the definition of the effective samples.
Is the effective sample?
Yeah, it's the effective samples. So let's see.
It's a fact sample or is fact sample rate? I didn't see. I didn't remember we care about the effect number of effect samples, but the ratio of.
It's the number of the effective samples, I think.
What does it mean?
Effective samples for elliptical slice sampling.
Yeah, let me check. So this is the experiments and the results. So this is how it says the effective samples from the log likelihood traces using RCODA. I don't know what does this mean.
Oh, it's just to calculate the effective number of samples. Like you might collect 10,000 posterior samples, but the effective number of samples is like how it is amounts to, I mean, equivalent to the number of independent samples.
So how they calculate the number of effective samples?
There is some formula. So basically for Monte Carlo algorithm, the samples you generated are not independent. So they contain duplicated information. So like 10,000 examples, they might just correspond to 100 independent samples. So this was the effective sample size mean.
Oh, okay.
But here I'm just curious to know if it is the effective sample size. So it is the effective sample size of elliptical slice sampling only.
Yeah, they have like 4 bars here.
Yeah, they have 4 bars, but which it is for whose effective sample size?
There are 4 methods
So
here.
there are 4 methods here. The first one is for the elliptical slice sampling.
Okay.
Yeah, and so when the dimension is high, the control point image almost failed. And the second row is the CPU time. They also give the description about how they calculate the CPU time.
So what's the largest dimension in their data set?
The largest dimension is this one, is 10. This is one.
R10, right?
See, yeah, R10, yeah.
Did they say how large is the dimension?
How large is the dimension?
It is 100, 1,000, or?
It's just 10 dimension.
Just 10 dimension.
Yeah.
That means just a 10 dimensional multivariate Gaussian plot.
Yeah.
And then this should be input dimension, right?
Yeah, this is the input dimension. The data size is 200.
Every data set consists of 200 data points, or?
Yeah, I think for all the 10, the input from dimension from 1 to 10, they all use the 200 data size. But they didn't mention whether it's training or testing. They just say the data size is 200.
Okay.
Yeah, and then the second row is the CPU time. So for the CPU time, the elliptical slice sampling is comparable to the line slice from dimension 1 to 10, but they are both greater than the other two methods, the neo MH and the control point MH. But as the dimension gets higher, the control point MH, the CPU time is larger than the elliptical slice sampling and the line slice. And also the effective samples, they almost 0. And for the classification and the Cox process task, the elliptical slice sampling is the CPU time is better than the line slice. And they also mentioned on the USPS classification program, control variables is very slow and no meaningful results over 10. So that's why this place, there is no bar here. And they also, the third measurement is the number of likelihood evaluations. But I am not sure why they need to use this measurement.
They just compare their test log likelihood.
This is the number of the likelihood evaluations. Like how many times they evaluate the likelihood.
Then this number is the lower the better, right? Because evaluating the likelihood is costly for if it's a large data set.
Yeah, I think so. But the number of evaluations for the elliptical slice are worse than all other 3 methods.
They have to do a lot of more evaluations than the others.
Yeah.
Okay, but did they compare with the log likelihood? They just compared the log likelihood with
No.
the variable method.
Yeah, they just compare the log likelihood for the Gaussian process regression. That's the only log likelihood.
That's weird.
Oh, they also mentioned there is a supplement for the experiments, but I just Googled and I found nothing. I didn't find the supplement they mentioned about.
Okay. Yeah, I'm kind of like previously I put a strong hope on this algorithm. Hopefully it can address our problem, but right now I'm not sure. And they also didn't compare with the Hamiltonian Monte Carlo sampling, right?
No.
I think even more straightforward way to implement is use HMC. But in our model, HMC doesn't give good performance.
Mm-hmm.
Okay. Any question? Any comments?
From what we have seen here, like the idea of this paper is, I'll use the word simple, but sometimes simple is good. But I don't get the point that it's like superior than any other methods. Like it jumped to some area and then shrink it back. What did they claim the advantage of this algorithm over others? They could automatically adjust the step size.
Yeah, they just said it can automatically search over the step size.
That's the only thing they solve by this algorithm.
That's the motivation.
Yeah, maybe because
also,
you start from uniform sampling and then you try to gradually shrink the range. So as long as you stop shrinking early, you're able to find a new sample distant away from the current sample.
But I didn't see why it could be more like efficient or could explore more of the range. Like HMC, they
So
have
basically,
created.
if you run MCMC, you want to more efficiently explore the whole sample space. Like we use metropolis Hastings, like using condition Gaussian, you have to tune the step size to be very small. That means every time you just jump a little bit distance away from the current sample. And so you can imagine that your exploration will be very slow. But here, this method is trying to, okay, I'm gonna first jump quite distant away to check if my proposal is good. If my proposal is not good, I'm gradually shrink the range until as long as find out one proposal, I stop here. It's like, okay, I'm gonna first explore space in a far away range, in a sporadic range, and if I can hit a proposal, okay, I'm got a new proposal. Otherwise, I try to shrink the range until I find one. So you can expect on average every time it moves more distant away from the current example, if you compare it with the simple metropolis Hastings method.
Could I share the whiteboard? I want to draw something.
Yeah, you might need to stop sharing and you can let Zhimeng to share the whiteboard.
okay.
So, for example, a distribution like this. The problem of this method, I mean, is that if we happen to jump out to this area, or I mean, for extreme case here, like we originally were here with a high probability area, and our sample will be we have to sample this point, the candidate point, but this is a very low probability area, then it will start to jump back. But in HMC, if we happen to jump here, it will follow the gradient and to exploit not HMC yet. It will follow the gradient and start to exploit this area. So for the current method is like I will try this area, and try this area, and see if I could find a high probability area. But most likely you won't be able to find, especially if the distribution is like a sparse, you won't be able to find a high probability area distance away if you didn't follow the gradient at all.
I'm not saying it will be better than HMC.
Yeah, so I'm wondering the like the advantage of this method. Just to adjust how long you automatically adjust how long you jump.
Yeah, it's like if you compare to like simple MH, like if you use the conditional Gaussian, right? So you have to tune the step size. If you start from here, and every time you just draw a sample here, you want to ensure a good acceptance. But if you use this elliptic slide sampling, you can imagine that, okay, I'm gonna run them starting from a large range. I might draw a sample here, right? And I just test. If I can pass the test, okay, I have already obtained a sample quite far away from the original sample, from the previous sample. If it's not, I try to shrink the range until at some place, if I can find a new sample here, it is still like more distance away from the sample generated by MH. But if you're saying, okay, as compared with HMC, which follows the gradient to find high density regions, I wouldn't say so. I mean, it is better, it is more efficient.
So for this kind of method, if we happen to find this location, then most likely we'll get trapped here, right? Because the probability is so high, then you won't be able to. It is very hard to find a area that has a higher probability than this point.
Yeah, according to their.
If you use high density, yeah, but it still has a chance, like because is log P of y is equal to log L plus some log U, right? U is a uniform distribution between 0 and 1. You're actually subtracting the current log likelihood. So, but you can imagine that, okay, I'm gonna gradually explore the area in this way. But if your current sample is staying here, you have more chance to get a sample here and get a sample here, rather than, okay, every time I just need to explore here and explore here. If you use metrology histine, because the step size alpha is fixed, right? But obviously we want the step size in this low density region, the alpha should be large, right? And for high density region, you might need the alpha to be small. It's kind of adaptive. I mean, the advantage is that they kind of adaptive. They want to search from the large range and narrow down to smaller range according to the position of the current sample. They don't want to fix how far away you're gonna jump from the current sample. But conceptually, I mean, if you compare it with the HMC, I don't see the reason it will be better than HMC. Perhaps in some region like your gradients, you have something like that. You follow the gradient won't tell you how much you should go away. But actually, I don't know. At least for the problem we have done, like the physics informed Gaussian process, HMC doesn't work. Okay, any other question? Okay, thanks. That is a good presentation. But next time, you should give a better resolution of your slides. It looks a little bit weak. And also, we'll walk through the Markov chain Monte Carlo sampling in our class. I mean, next time you should give a more rigorous proof of the detailed balance, especially for the new MH method. I would like to see more rigorous proof. Okay, and Thanks, everyone. And I think on Friday, John will present using physics-informed neural network to find PDEs from data. Okay, see you on Friday.
Thank you.
Thank you.